You know, there's a secret language being spoken all around us every single second. It's the language of change, and it's written in the food we eat, the things we build, even the air we breathe. So let's figure out how to read it together.
All right, let me ask you something. What in the world could sour milk, a rusty nail, and just taking a deep breath possibly have in common? I know, they sound totally random, right? But believe it or not, they are all connected by one amazing secret.
Well, the answer is they're all speaking that same language of change. Whether it's milk going sour in the summer, or an old iron pan getting rusty, or food cooking on the stove, heck, even our own bodies digesting a meal, in every single one of those cases, something completely new is being made.
Okay, so what is this invisible force that ties all these things together? To figure that out, we gotta zoom in a little closer and see what's really going on when that milk turns or that nail rusts.
And here's the big idea. In every single one of those examples, the stuff you started with, it's not the same anymore. Its fundamental identity has changed. That milk isn't just milk, right? It's something sour and curdled. That iron isn't just shiny iron, it's that rusty, flaky stuff. And anytime you see that kind of fundamental change, that's it. You're looking at a chemical reaction.
But how can you be sure? I mean, how do you know a chemical reaction is happening? Well, it turns out they leave clues behind, kind of like a crime scene. So let's put on our detective hats and learn how to spot the evidence.
So, there are basically 4 big clues you want to look for. First, you might see a change in state, like a liquid suddenly becomes a solid. Second, a change in color is a dead giveaway. Third, if you see bubbles or fizzing, that means a gas is being created. And finally, a change in temperature, if something gets hot or cold all by itself. See any of those? Yeah, chances are you've got a chemical reaction on your hands.
And this is such a great example. The source material gives us this awesome image of a magnesium ribbon burning. It says it has a dazzling white flame. Boom, there's your change in color and temperature. And then it changes into a white powder. And there's your change in state. It's like all the clues rolled into one. Just perfect.
All right, so we're getting good at spotting these changes. But how do scientists actually, write this stuff down? They can't just describe it every time. They need a shorthand, a precise recipe. And that's exactly what we're going to look at next.
I mean, you could write it out like a full sentence, but look at that. It's just long and clunky. It gets the job done, but it's not very efficient, right? Scientists needed something way better. So here's a much cleaner way to do it. It's called a word equation. Look how simple this is. Magnesium plus oxygen, and then that arrow, which basically means turns into, magnesium oxide. So much easier, right? That arrow is super important. It shows you the direction of the change. And this simple setup gives us 2 really important terms we need to know. The things you start with, on the left side of the arrow, those are your reactants. And the new stuff that gets made, on the right side, that's your product. It makes sense, right? Reactants react to make products.
Okay, but we can make it even more concise. This is the final step. We swap out the words for the actual chemical symbols. And this is the real deal, the chemical equation. This is the universal language of chemistry. A scientist in Tokyo and a scientist in Rio can look at this and know exactly what it means. It's pretty powerful.
Okay, but before we go any further, there is one non-negotiable rule. It's a fundamental law of the universe that you absolutely cannot break when you're writing these equations. And honestly, it might be the most important thing we talk about today. It's all about balance.
It's called the law of conservation of mass. And it's actually a pretty simple idea. You can't just make stuff appear out of thin air, and you can't make it vanish. Nothing is ever truly lost in a chemical reaction. Think about it like you have a box of Legos. You can take them apart and build something new, but you still have the exact same number of Lego bricks you started with. Atoms work the exact same way. So keeping that Lego rule in mind, let's play detective again. Take a look at this equation right here. This shows iron reacting with water. So the question is it balanced? Are all the Lego bricks accounted for on both sides?
So what do you do when it's not balanced? Well, thankfully, there's a step-by-step method to fix it. First, you just make a list of all the atoms on each side. Then, you find the ugliest, most complicated molecule in the whole thing, and you start by balancing the atoms in that. From there, you just work your way through the other elements, one by one. And at the very end, you do a final head count just to be sure. Let's give it a shot.
Okay, let's do that first step with our iron equation. Let's see, on the left, we've got 1 iron atom. But on the right, wait, there are 3. Uh-oh, that's not balanced. How about oxygen? 1 on the left and 4 on the right. Yikes, also not balanced. So yeah, this equation is definitely breaking the law. So how do we fix this? We use something called coefficients. They're just big numbers you put in front of a molecule, and they basically act like a multiplier. It's like saying, I have 3 of these, or 4 of those. So if we put a 3 in front of the iron, a 4 in front of the water, and another 4 in front of the hydrogen, let's check our work. Now we have 3 irons on both sides, 8 hydrogens on both sides, and 4 oxygens on both sides. Perfect. It's all balanced. The law is happy.
Awesome. So now that we've got the rules of this secret language down, we can start to have some fun with it. Let's look at a really common type of reaction, one that you probably see all the time without even realizing it. It's called a combination reaction.
And a combination reaction is, well, it's exactly what it sounds like. You take 2 or more things, they react, and they combine to make one single bigger thing. You know, A plus B comes together to make AB. Super straightforward.
So what? Why is this cool? Well, let me ask you this. Have you ever seen a freshly whitewashed wall? At first, it's kind of dull. But if you wait a couple of days, it gets this really nice, shiny, hard finish. Ever wondered why? You guessed it. It's a combination reaction happening right in front of your eyes.
Okay, so here's how it works. It's actually a 2-step process. First, to even make the whitewash paint, you take something called quicklime and you mix it with water. That's our first combination reaction, and it creates a new thing called slaked lime. That's the stuff you actually put on the wall.
But that's not the end of the story. This is where the real magic happens. For the next 2 or 3 days, that slaked lime on the wall is slowly, quietly reacting with the carbon dioxide that's just floating around in the air. It's a second combination reaction happening in super slow motion. And what does that slow motion reaction create? It makes something called calcium carbonate. And you might be thinking, okay, so what? Well, what is calcium carbonate? It's the chemical name for marble. Seriously, that shiny, hard finish on the wall is a paper-thin layer of actual marble, created just by reacting with the air. How cool is that? And that's the thing. Once you learn to read the secret language of change, you start seeing these amazing stories written everywhere you look.
I mean, really think about it for a second. That shiny new bike you leave out in the rain? An apple you cut open that turns brown? A bag of chicks that just goes stale? It almost feels like it's a universal rule, doesn't it? That things are just designed to break down? But what is actually happening on a molecular level?
Well, it turns out it's not just some random chaos, it's chemistry. It's actually a series of really predictable reactions, almost like steps in an intricate dance. And once you know the steps to that dance, you can start to understand it, and maybe even control the process. So let's learn the moves.
Okay, so to really get how things fall apart, we're going to need a chemical toolkit. We're going to go over 4 basic types of reactions that are pretty much the building blocks for everything else we're going to talk about today. First up in our toolkit is decomposition. I like to call this one the breakup. It's actually pretty simple. You have one single complex compound that basically decides it's had enough, and it splits up into simpler parts. You can think of it like the compound AB, breaking apart into A and B, each going their separate ways. And this kind of thing happens in the real world constantly. Take limestone, for instance, which is mostly calcium carbonate. It doesn't just crumble on its own. It needs a little push. Something like heat. That energy is what breaks the chemical bonds, and poof, you're left with 2 totally new substances. All right, next up is displacement. Let's call this one the cut-in. So picture this. Element A walks up to the happy couple BC. Now, if A is more reactive, more attractive on a chemical level, it can just cut right in and steal C for itself, leaving poor B all alone. It's pure chemical competition. And here is a perfect example of that. See, in the world of elements, some are just more reactive than others. It's kind of like a popularity contest. Zinc happens to be more reactive than copper. So if you put a piece of zinc into a copper sulfate solution, the zinc essentially says, "Excuse me," and just kicks the copper right out so it can bond with the sulfate instead. Our third tool is double displacement, and you can probably guess this one. I call it the partner swap. Just imagine 2 compounds, let's say AB and CD, meet on the dance floor. They look at each other and decide, hey, let's trade partners. A pairs up with D and C pairs up with B, and just like that, you've created 2 entirely new couples or compounds.
A classic, textbook example of this is when an acid and a base neutralize each other. It's a perfect partner swap. The hydrogen from the acid gets together with the hydroxide from the base to make water, and the leftover sodium and chloride pair up to make, you guessed it, simple table salt. And finally, we have the real powerhouse, the redox reaction. This is the give and take.
This reaction is all about exchanging electrons. One substance loses electrons, we call that oxidation, and at the exact same moment, another substance has to gain those electrons, and that's called reduction.
And seriously, don't underestimate this one. Redox reactions are absolutely everywhere. The very breath you're taking right now, that involves a redox reaction. The fire that cooks your food, the battery that's powering your phone, it is all driven by this constant give and take of electrons. It's the engine of our world.
All right, so we have our toolkit packed. Now, let's put on our detective hats and apply this knowledge to a real-world crime scene, the rusty car.
Corrosion. It's probably one of the most visible and definitely most costly examples of chemistry just breaking things down. It's this relentless, slow, silent process that turns strong, useful metal right back into its weaker, original, earthy form.
So, which tool from our kit explains what's going on with rust? It is a classic redox reaction. The iron is being oxidized, which, remember, means it's losing electrons to the oxygen in the air. Water helps out here, acting as a catalyst that just speeds the whole process along. And the result is that flaky, reddish-brown stuff we all know and hate, rust. Let's move from the garage to our next case file. This time, we're heading into the kitchen. We are going to investigate the spoiled snack and the science of rancidity. You know that weird, sharp smell you get from old nuts or a bag of chips that's been open too long? That is rancidity. It's what happens when the fats and oils in our food get exposed to air for too long. And the chemical culprit behind it all? Well, it should sound pretty familiar by now. It is the O in redox, oxidation. That smell, it's literally the scent of a chemical chain reaction happening. Oxygen is breaking down the fat molecules, creating these new compounds that our noses and our tongues find, well, pretty disgusting. And the amazing thing is, it's the same fundamental process as rust. It's just happening to your snack instead of your car. Okay, now for the best part. Because knowing how things fall apart, well, that gives us the power to stop it from happening. We can actually use chemistry to fight back against chemistry itself. And the solution for both rust and rancidity is surprisingly simple when you get down to it. You just have to block one of the key ingredients in the reaction. If iron can't get to oxygen and water, it can't rust. It's that simple. If the fats in your food can't get to oxygen, they can't go rancid. And here's how we actually do it. Painting a car or greasing a bike chain, that's just a simple physical barrier. But galvanization, now that's even more clever. It coats steel with zinc. Remember how we said zinc is more reactive? Well, it essentially sacrifices itself. The zinc corrodes first to protect the iron underneath. How cool is that? That's a displacement reaction being used as a defense. And for food, the strategies are pretty similar. An airtight container is basically a coat of paint for your snacks. Putting things in the fridge, that just slows the reaction rate way down. And you know that air in your bag of potato chips? That's not just air, it's usually nitrogen. It's an inert gas that displaces all the oxygen, which stops the oils on the chips from oxidizing and going stale.
So you see, these chemical reactions, decomposition, displacement, and especially redox, they aren't just abstract ideas from a textbook. They are actively, silently shaping our entire world, from the bridges we drive across to the food we eat. So the next time you see a rusty nail or seal up your leftovers, you'll know the hidden chemistry that's at play. And the real question is, now that you know the steps to the dance, where else are you going to start to see it?